At the very edge of our solar system sits a region of space that gets hotter than the surface of the sun. Not a little hotter, up to 8 times hotter, somewhere between 30,000 and 50,000 Kelvin, hot enough that scientists gave it an informal nickname, the Wall of Fire. 2 machines built in the 1970s, running on computers slower than a digital watch, flew straight through it. Neither one burned, neither one broke. Both kept sending signals home from the other side, and one of them is now, in 2026, closing in on a distance so vast that a message sent from Earth takes a full 24 hours just to arrive. This is the story of what those 2 machines found at the edge of everything we call home, why a region hotter than a star didn't destroy them, and why the mystery they uncovered out there still doesn't have a complete answer. Most people picture the solar system as a fixed set of planets orbiting the sun, and then nothing, an empty edge where our neighborhood simply stops and the rest of the galaxy begins. That picture is wrong, and it has been wrong for over half a century. The sun is not a quiet lamp sitting at the center of everything. It is constantly boiling off charged particles, mostly protons and electrons, blasting them outward in every direction at hundreds of kilometers per second. This outward stream is called the solar wind, and unlike the wind on Earth, it does not slow down and stop near any particular planet. It keeps traveling past Mercury, past Earth, past Mars, past Jupiter and Saturn, past Uranus and Neptune, past Pluto and the Kuiper Belt, continuing outward to roughly 3 times the distance of Pluto before it finally starts running out of push. As that stream of particles travels, it drags the sun's magnetic field along with it, and together they inflate an enormous protective bubble around the entire solar system. Scientists call this bubble the heliosphere, and everything you have ever known, every planet, every moon, every asteroid, every spacecraft that has ever launched from Earth until very recently has lived its entire existence inside that bubble. But a bubble, by definition, has an edge, and the space just outside it is not truly empty either. Interstellar space is filled with its own thin mixture of gas, dust, and charged particles left behind by the winds of other stars and the shock waves of ancient supernova explosions from millions of years ago. That thin mixture is called the interstellar medium, and it is constantly drifting through the galaxy under its own pressure. Somewhere far beyond Pluto, these 2 forces meet head-on. The outward push of the sun's own wind collides with the inward press of interstellar space, and where they collide, they do not simply blend together peacefully. They shove against each other, and a genuine boundary forms between them, a place where the properties of space itself change dramatically over a relatively short distance. Scientists named this boundary the heliopause. In the most literal sense, the heliopause is the edge of the sun's authority over its own surroundings, the precise line where our star's influence ends and the broader galaxy takes over. For decades, this boundary existed only in theoretical models and equations. Nobody actually knew what it would look like, or feel like, or measure like, until something built by human hands actually traveled there and crossed it. The 2 machines that eventually answered that question were never designed for this job in the first place. Voyager 1 and Voyager 2 launched from Cape Canaveral in 1977, 16 days apart, with Voyager 2 actually lifting off first on August 20th. And Voyager 1 following on September 5, but taking a faster trajectory that let it overtake its twin. Their original assignment was a 4-year tour of Jupiter and Saturn, meant to photograph the outer planets and their moons, and then quietly finish their mission. Voyager 2 was given the more ambitious route, a rare planetary alignment that let it visit all 4 gas giants, Jupiter, Saturn, Uranus, and Neptune, a gravitational assist opportunity that only comes around roughly once every 176 years. Voyager 1 took the faster, more direct path through Jupiter and Saturn alone, sacrificing Uranus and Neptune for extra speed. Both spacecraft completed their planetary tours successfully, Voyager 1 finishing its Saturn flyby in November 1980, technically closing out the mission they were built for. Neither one stopped. Both kept flying outward, kept transmitting data, kept operating year after year, long after their planned careers were supposed to be over, because nobody had built a hard stop into their design, and nobody at NASA was in any hurry to turn off machines that were still working and still generating good science. That unplanned bonus decades of operation is what eventually carried both spacecraft to the one place nothing human-made had ever been before, the actual boundary of the heliosphere itself. Voyager 1 got there first. In August 2012, after 35 years of continuous flight, its instruments registered something dramatic and sudden. The steady flow of solar wind particles that had surrounded the spacecraft for its entire existence abruptly dropped away. And in the same moment, the count of galactic cosmic rays, the high-energy particles that originate from outside the solar system entirely, spiked sharply upward. On August 25, 2012, Voyager 1 had crossed the heliopause. It became the first object ever built by human beings to leave the bubble and enter true interstellar space, a milestone that took engineers months to fully confirm once they combed through the data. Voyager 2 made its own crossing 6 years later in November 2018, at a completely different location along the boundary because the two spacecraft had been traveling in different directions since their planetary tours ended. Voyager 1 heading up and out of the plane of the solar system, Voyager 2 heading down and out in the opposite direction. Voyager 2's crossing mattered in a way Voyager 1's could not, because Voyager 2 still had a working plasma instrument on board. Voyager 1's equivalent instrument had failed decades earlier, back in 1980, which meant scientists could only infer what was happening around it indirectly through other measurements. Voyager 2 could take a direct reading of the plasma itself as it crossed the boundary, and what it measured is the number that eventually made headlines around the world. When Voyager 2's plasma instrument returned its reading from the heliopause, the temperature came back somewhere between 30,000 and 50,000 Kelvin. To put that in perspective, the surface of the Sun itself sits at roughly 58,100 Kelvin. The plasma sitting at the boundary of our own solar system, a region most people assume should be cold and empty and uneventful, was reading several times hotter than the surface of a star. It was, in the most literal sense, a science headline could offer, hotter than the Sun. This is where the informal nickname came from, the Wall of Fire, a boundary sitting quietly in the dark at the edge of everything, radiating heat that would vaporize almost anything on Earth within seconds of contact. And this is exactly the point in the story where the obvious question demands an answer. If that region of space really is up to 8 times hotter than the surface of the Sun, how did two machines built with 1970s technology, running on computers with less processing power than a modern calculator, fly directly through it and come out completely intact, still transmitting, still functioning, still sending data home decades later? The honest answer required scientists to explain something most people, understandably, have never been taught to separate: the difference between temperature and heat. Temperature and heat sound like the same concept in everyday language, but to a physicist, they measure two very different things. Temperature measures how fast individual particles are moving, their raw kinetic energy at the smallest scale. Heat measures something else entirely, the total amount of energy that actually gets transferred into an object when those particles strike it. A region can have blisteringly high temperature and still transfer almost no heat at all if there are so few particles present that almost nothing ever actually makes contact with anything solid passing through. The easiest way to feel this difference is with something everyone has already experienced. Open a hot oven, and you can hold your hand in the air just inside it for a second or two without any real harm, because air is a poor conductor and there simply aren't enough air molecules striking your skin at once to transfer much energy. Touch the metal oven rack sitting at that exact same temperature, though, and you will burn yourself instantly because metal is dense and packed full of atoms that transfer energy into your skin the moment they make contact. Same number on the thermometer. Wildly different outcome, depending entirely on how many particles are actually delivering that energy and how efficiently they deliver it. Now stretch that same idea out to its most extreme version, and you have the heliopause. The plasma at the edge of the solar system genuinely is moving at speeds consistent with a 50,000 Kelvin environment. That part is real, and it was measured directly. But the region is one of the emptiest environments ever recorded by any instrument built by humans. The individual particles are moving incredibly fast, but there are almost none of them in any given volume of space, so a spacecraft passing through barely gets touched by anything at all. Voyager 1 and Voyager 2 flew through a region with a higher measured temperature than the surface of the Sun and experienced something closer to a light, harmless breeze than a wall of flame. The nickname captures the drama of the number. It does not capture the actual physical experience of passing through it, which barely registered on either spacecraft's hull at all. Part 5. The Mysteries. The Crossing Left Behind. If the temperature reading were the only surprise from these two crossings, this would already be a remarkable story. It is not the only surprise. The heliopause crossings raised at least 3 genuine open questions that scientists are still working through today, more than a decade after Voyager 1's first crossing, and years after Voyager 2 confirmed the pattern from a different angle. The first surprise was the heat itself. The plasma temperature measured at the boundary came back higher than the leading theoretical models had predicted before either spacecraft arrived. That gap between prediction and measurement tells researchers that the collision between the outgoing solar wind and the incoming interstellar medium is more violent and more energetic than existing theory had captured, and that particles at the boundary are being compressed and accelerated in ways the models had not fully accounted for. Decades of textbook diagrams describing the edge of the solar system had to be quietly revised because 2 aging spacecraft actually went there and measured the real thing instead of relying on extrapolation. The second surprise was stranger and remains genuinely unresolved. Both Voyager 1 and Voyager 2 detected that the magnetic field just outside the heliopause, out in true interstellar space, was aligned in roughly the same direction as the magnetic field just inside the bubble, still under the Sun's influence. That alignment should not exist. The sun's magnetic field and the broader galactic magnetic field have no obvious physical reason to point in the same direction at the exact location where one meets the other, and yet both spacecraft found evidence pointing toward exactly that kind of alignment at their respective crossing points. Either this is an unusual coincidence tied to the specific geometry of where each spacecraft happened to cross, or there is something about how this boundary actually functions, some mechanism connecting the two magnetic environments that current theory does not yet explain. Scientists have not settled which explanation is correct. The third surprise came from comparing the two crossings directly against each other. Voyager 1 and Voyager 2 crossed the heliopause at different distances from the Sun, despite crossing only 6 years apart, which tells researchers that the heliosphere is not a neat, symmetrical sphere sitting evenly around the solar system. It breathes. It physically expands and contracts in step with the Sun's roughly 11-year activity cycle, swelling and shrinking as solar activity rises and falls. It is also likely squeezed on one side and stretched out on the other by the pressure of the interstellar wind coming from a particular direction, as the entire solar system moves through the galaxy, giving the heliosphere an asymmetrical, almost comet-like shape, with a long trailing tail streaming out behind us rather than a clean, spherical boundary. 2 data points collected 6 years apart from the only 2 spacecraft that have ever made this specific journey are, at this moment, the entire body of direct evidence scientists have to work with. And every single one of those data points forced a revision to what was previously assumed to be settled. While all of this scientific value keeps flowing back to Earth, the machines producing it are visibly, measurably dying, and the story of their slow decline has become just as compelling as the discoveries themselves. Both Voyager spacecraft are powered by radioisotope thermoelectric generators, devices that convert the natural radioactive decay of plutonium-238 into usable electricity. At launch in 1977, those generators produced approximately 470 watts of power. There is no refueling this kind of system, no way to replace the plutonium, no repair crew that can ever reach a spacecraft this far from Earth. The power output simply declines steadily and permanently as the plutonium decays, losing roughly 4 watts of capacity every year without exception. By 2026, nearly half a century after launch, Voyager 1's generators are producing somewhere in the range of 220 to 250 watts, barely enough electricity to power a couple of household light bulbs, and that shrinking supply has to run everything on the spacecraft at once. Its heaters, its transmitter, its onboard computer, and whatever science instruments are still switched on. Engineers at the Jet Propulsion Laboratory have spent the last 2 decades making increasingly difficult decisions about what to sacrifice next in order to keep the spacecraft alive a little longer, systematically shutting down non-essential systems and instruments one at a time in a carefully sequenced, irreversible retreat. Voyager 1 was 1 launched carrying 11 scientific instruments. As of 2026, only 2 remain switched on and functioning. The magnetometer, which measures magnetic fields, and the plasma wave subsystem, which detects the density and behavior of charged particles in the surrounding interstellar medium. Everything else has been deliberately powered down over the years to conserve the shrinking supply of electricity. The most recent casualty came in April 2026, when NASA engineers deactivated Voyager 1's low-energy charged particle instrument, the LECP, specifically to prevent a catastrophic undervoltage event that could have damaged other critical systems on board. One science writer covering the decision described it bluntly as a surgical amputation, a necessary sacrifice of one working part, to keep the rest of the spacecraft's heart beating for as long as possible. The instrument had been detecting electrons, ions, and cosmic rays moving through interstellar space, real and valuable data, and NASA chose to trade that data away in exchange for more operating time overall, with the possibility of switching it back on briefly in the future if the situation allows. The spacecraft's communication link has also become visibly fragile in recent years, not just its instruments. In October 2024, Voyager 1's primary X-band radio transmitter shut down unexpectedly after an onboard fault protection system triggered in response to a heater being switched on. The transmission rate dropped, engineers scrambled to locate the weakened signal, and when the transmitter cut out entirely a few days later, the spacecraft's own safety systems automatically switched it over to a backup S-band transmitter, a piece of hardware that had not been actively used since 1981. For a stretch of weeks, humanity's most distant object was talking to Earth, using a radio system from before most of its current ground control team had even been born. Engineers eventually managed to reactivate the primary X-band transmitter and resumed full data collection by mid-November 2024. But the episode was a stark reminder of exactly how little margin for error remains on a machine with, in the words of Voyager project manager Suzanne Dodd, no working backups left for its critical systems. Everything on board now single string, meaning any single failure in the wrong component could end the mission permanently with no way to recover. Even the ground side of this relationship has run into trouble. Deep Space Station 43, the massive antenna facility in Canberra, Australia, and the only dish on Earth powerful enough to send commands to both Voyager spacecraft, went offline for major upgrades between May 2025 and February 2026, with only a handful of limited operational windows open briefly in August and December 2025. For most of that stretch, NASA could still listen to Voyager 1 and Voyager 2 through other antennas in the Deep Space Network, but it could not reliably send new commands to either spacecraft, leaving both probes essentially running on autopilot, trusting decades-old onboard programming to keep them safely oriented and alive until human controllers could re-establish full contact. Facing a power supply that will only ever get smaller, never larger, NASA's engineering team made a decision in 2026 that amounts to one of the riskiest interventions attempted on either spacecraft in the entire mission's history. It is an operation the team internally refers to as the Big Bang reconfiguration, and it is not a small patch or a minor software tweak. It is a complete, remote rewiring of each spacecraft's internal power distribution hierarchy, executed entirely through commands sent across billions of miles of empty space, swapping out older, more power-hungry electrical pathways for leaner alternatives that draw less current from the dwindling supply. The risk involved is genuinely severe, not exaggerated for dramatic effect. If anything goes wrong during the transition, specifically if one of the spacecraft's heaters fails to maintain the correct temperature while systems are being reconfigured, the hydrazine fuel lines that feed the maneuvering thrusters could freeze solid in the roughly minus 270 degrees Celsius environment of interstellar space. If those fuel lines freeze, the thrusters that keep each spacecraft's antenna precisely pointed back toward Earth would stop functioning entirely. And without that precise pointing, the signal home would be lost permanently, turning either Voyager into a silent, derelict object drifting through the galaxy with no way for anyone to ever hear from it again. Rather than risk both spacecraft simultaneously, NASA structured the reconfiguration as a staged test. Voyager 2, which currently has slightly more power margin to work with than its twin, was scheduled to undergo the procedure first, in May 2026, essentially serving as the test case for the entire approach. If Voyager 2 survived the transition intact, Voyager 1 was scheduled to follow with its own version of the same reconfiguration in July 2026. It is, by any reasonable description, a calculated gamble performed on two of the most historically significant machines humanity has ever built, undertaken specifically because the alternative, simply continuing on the current trajectory of power decline without intervention, guarantees an even earlier and more certain end to both missions. Against this backdrop of shrinking power and mounting risk, Voyager 1 is now approaching a distance milestone that no human-made object has ever reached in the history of the species. NASA has confirmed the exact moment. On November 18, 2026, at Tucson or 16:07 a.m. Pacific Standard Time, Voyager 1 will be 799,996 miles from Earth, equal to roughly 9 billion kilometers, a distance so vast that it represents exactly one light day. The distance light itself travels through the vacuum of space in a full 24 hours. At that exact moment, Voyager 1 will be 6 times farther from the Sun than Neptune, humanity's most distant working machine, crossing a threshold that has never before been crossed by anything we built. The practical consequence of that distance is almost impossible to fully absorb. Suzanne Dodd, the Voyager project manager at the Jet Propulsion Laboratory, has described it in the simplest possible terms. If she sends a command to the spacecraft and says good morning at 8 in the morning on a Monday, she will not receive Voyager 1's response back on Earth until roughly 8 in the morning on Wednesday, because the message takes a full day to travel outward at the speed of light, and Voyager 1's reply takes another full day to travel back. Every single conversation with the most distant object in human history now unfolds across a round trip of 48 hours, an ordinary Monday morning greeting stretched out across the width of an entire interstellar gulf. Voyager 1 continues moving outward at approximately 38,000 miles per hour, or about 61,000 kilometers per hour, heading generally toward the constellation Ophiuchus, a direction it has held steady since leaving the plane of the planets decades ago. At that speed, current NASA projections estimate it will pass within roughly 7 light-years of the faint red dwarf star Gliese 4145, sometime around the year 40,272, an almost unimaginable span of future time during which the spacecraft will simply keep drifting, silent and unpowered, long after every human alive today, and likely every human civilization as we currently understand it, has come and gone. Despite everything Voyager 1 has already achieved, despite the heliopause crossing, despite the light day milestone, despite 49 years of continuous operation far beyond anything its original engineers ever expected, it is important to be precise about exactly what has and has not happened. Crossing the heliopause and leaving the heliosphere does not mean Voyager 1 has left the solar system in any complete sense. It means the spacecraft has left the bubble of the sun's magnetic field and solar wind. The sun's gravitational influence extends dramatically farther than that boundary, reaching out to the Oort cloud, an enormous shell of icy bodies loosely bound to the sun by gravity that marks the true final gravitational edge of our solar system. By that stricter definition, Voyager 1, despite 49 years of flight and despite being the single most distant human-made object in existence, has barely stepped off the front porch of its own solar system. Current estimates suggest it will take roughly 300 more years of continuous travel just to reach the inner edge of the Oort cloud, and after that, tens of thousands of additional years to actually pass all the way through it and reach truly open interstellar space in the fullest gravitational sense. The spacecraft that broke the heliopause in 2012, that measured a wall of fire hotter than the sun and survived it without a scratch, that is now closing in on a distance where light itself needs a full day to keep up with it, has still, by the most rigorous possible standard, not finished leaving home. Here's what actually happened, stripped down to what the instruments confirmed rather than what the nickname implies. A boundary exists at the edge of our solar system where the outward push of our own star collides with the pressure of the entire rest of the galaxy. And that collision generates plasma temperatures that genuinely exceed the surface of the sun itself. Two machines from 1977, running on fading nuclear power and computers, a small fraction as capable as the phone in your pocket, flew directly through that boundary and kept working, saved only by the fact that the region is too empty to transfer meaningful heat despite its blistering temperature. What they measured there, rewrote the models, exposed a magnetic field alignment nobody can fully explain, and revealed a heliosphere that breathes and stretches rather than sitting still. And now, decades later, with instruments failing one by one and engineers gambling on a total power rewiring just to keep the signal alive, Voyager 1 is about to cross a distance so vast that a simple good morning takes 2 full days to complete as a conversation. The wall of fire has already been crossed. The mystery of exactly how it works has not.